Our second application of linear simultaneous equations comes from statics. And like with the electric circuits, you don't have to worry too much about the details of how we come up with the equations, but I do want to show you a little bit of the background and what those equations mean. So in this case, we've got a 1,000-pound weight. We've supported it with 3 cables that are attached to the ceiling, and we want to find the tension in each cable. So since there are 3 unknowns, we need 3 linear equations to do that. So here's the geometry. This cable we call cable 1 is attached here, 4 feet away from the origin in both the X and the Y directions, and the origin is 10 feet above where we actually hang the weight. Cable 2 position is also fixed at this location, and cable 3 is kind of the variable one. We can attach this anywhere, so we'll say along the ceiling there's a beam running in that direction. We can attach this anywhere along the beam. Now, we can now take each one of those forces in the cables and know that those tension forces have to act along the direction of the cable. So again, in statics class, you'll learn how to take each of these and divide it into its X, Y, and Z components. So, for example, cable 1, its T1 is in the direction of the cable, but we can divide it into 3 components in the X, Y, and the Z directions. And you can do the same thing here for cable 2. Again, components X, Y, and Z. Cable 3, remember we said it's only in that YZ plane, so it does not have an X component. Also, depending on the distance we pick for D here, the length of the cable will change, and the length of the cable is equal to the length of the hypotenuse of the triangle, defined by the 10-foot vertical distance and D horizontal distance. So square root of 10 squared plus D squared, square root of that is the length of cable 3. And so T3Y and T3Z are based on that length. Okay. Now, once we know we have those components of the tensions, we can now apply equilibrium equations, which says that the sum of the forces in each of the 3 directions have to add up to 0. So what that means is that the X and Y components of the 3 cables have to balance each other out. The Z components of the 3 cables will all be upward, and they have to balance out a downward 1,000 pound of the weight. So our first equation, when we solve in the X direction, we take the components in the X, make them equal to 0. Of course, there is no X component for T3. In the Y direction, we have components in all 3 directions. They have to add up to 0. And in the Z direction, we have upward or positive components of all 3 of the cables, and we have a downward 1,000 pounds of the weight. That has to equal 0 as well. So now we can write these 3 equations in matrix form. Okay. Now, here's the solution in Excel. We start out by assuming a value of D. We calculate the length based on that equation, the square root of 100 plus D squared. And here is our coefficient matrix. So when we change the value of D, it will change the length, and we'll change these 2 components. Everything else stays the same. Our constant matrix is always going to be the same. And so here, what we've done is inverted this matrix, multiplied by C, and there's our answer. So those are the tensile forces in pounds. So in this case, when we attach the cable only 2 feet from the origin, cable 3 takes the most force, 658 pounds, while the other ones are 250 and 160 pounds. Okay, so that's one solution. Now again, you can try different values of D, and that's what you'll do for homework with MATLAB. Now let's talk about one of the things in the homework. It asks about the factor of safety. What the factor of safety really answers the question of how safe are these cables? How much would I increase the load before it would break? Well, first of all, you notice that the one that's most likely to break is always going to be the one with the greatest tensile force. In this case, that'll be cable 3. Now let's say that these cables have been tested and they're rated to hold 1,500 pounds each. then the factor of safety would be equal to 1,500 pounds divided by the greatest tensile force. So in this case, the greatest tensile force was 658, and so our factor of safety is 2.28. So that means, in theory, that we could hang not just 1,000 pounds, but 2,280 pounds before we would worry about that cable breaking. So again, in the homework problem, what you're going to do is set up an array of d values, calculate the factor of safety for each d, and then find the d that gives you the highest factor of safety. Now, a little bit of hint about that. We've used the max command before in MATLAB, so let's just review that for just a moment. And again, unrelated to that last problem, we'll just come up with this general array here, a row array that has 7 values. And so we input that in MATLAB. If we just use the max command and say b is equal to max of a, what it's going to do is search and find me the maximum value and return just that value. So again, if we have an array of factor of safety values and we just find the max, well, that we can find that. But now we want to know, well, maybe what length does that correspond to? So remember, if we define if we assign 2 variables with the max command, what we get are these 2 values. Now, of course, b is just the same. b is the maximum value of 12. But what 4 means is that's the index of the maximum value. And we can see that if we go back here, 1, 2, 3, the 4th value is the maximum value. And that's the second thing that we get out of that. So that little hint there will be helpful for solving the homework problem.